Hey folks, Quill18 here, and welcome to the continuation of our simple space shooter tutorial. In the last episode, we got our ship moving around a little bit. We can also rotate, but unfortunately, the rotation doesn't affect the up and downness. So let's talk about exactly why that is. If we go into our code, when we move up, we are writing directly to the Y, which is not what we want to do. We are going to have to affect our change here based on our rotation. We know the rotation that our ship is pointing in. Well, we could read it simply off the transform.rotation. That would be fine. What we need to do is this change in position, we need to change based on a rotation. So instead of writing directly to the Y, what are we going to do? It's really, really, really easy. So again, I'm going to continue my habit of creating a lot of temporary placeholder variables, sort of to make everything a little bit more explicit, but there's no reason we have to do it quite this way. So instead of writing directly to the Y, what we're going to do is we're going to create a new vector. Vector 3, this is going to be like the position change, also known as the velocity, I guess. It's sort of the change this frame, though, so it's not entirely accurate to call this velocity, but what the hell. So what we're going to do is we're going to create a new vector. And in this vector, the x component is going to be a 0, the y component is going to be this number we've already worked out, and the z is going to be a 0. The z is clearly going to be a 0 because we're not going to advance into the screen. Now, if I go something like position plus equals velocity right now, we're going to have exactly what we already had. Let's go ahead and test to make sure that's true. Forward, backwards, and this sort of weird, not quite right forward and backward. Okay, everything is fine. So what we're going to want to do, instead of adding our velocity vector here as is, we're going to take our rotation, which we can do either from this way, or I could use the rot because it's exactly the same thing. So let's do that. Our rotation, we're going to multiply by our velocity, and that'll be our position change. You have to do it in this order. The quaternion has to come first. You can't put the vector followed by the quaternion. It just doesn't work. Also, if you have a semicolon in the wrong place, whoops, that also won't work. There we go. Yeah, let's hit play. I'm going to hit up. I'm going to hit down. I'm going to turn left. I'm going to hit forward. Oh, baby, look at that. We got us a spaceship. Oh, yeah. Now, right now, the ship's speed and its ability to turn is controlled by those two variables. Now, by default, these were set up to be, I guess they're protected variables. If I set them to be public, a very cool thing starts to happen. In our player ship, in the inspector, we can change the numbers there. So in here, I can change it, say, 360. Now our ship will turn much faster. Vroom, vroom, vroom. Too fast? I don't know. You decide. I'm going to go ahead and put it back to 180. Actually, here's the thing. What if I decide, you know what? I want a really slow turning ship. I want to turn it at a rate of 90 degrees per second. And I go into my code here, and I change my rotation speed to 90. And I hit play. What's going to happen? Nothing. We still turn at super fast speeds. And the reason for that is, once you've made one of these things public, changing this number here only changes the default number, the default value of this I don't know, what do you call this attribute? Once it's in the inspector, sort of attribute, but this 90 only becomes the default. If I create a new player ship or new ship of any kind and give the player movement script to that new ship, it'll get a 90 in the rotation speed. But once I've changed this number here, it doesn't matter what I do over here. In fact, these can all be blank. Doesn't make a difference. So keep that in mind. If you've made something public, changing the numbers in the script over here will no longer actually affect the instance in your hierarchy. So sometimes I just leave everything protected and I just work on things from here because that's the way I kind of operate. I don't know. We'll go ahead and continue to do things the kind of Unity style where you have it in the inspector, and I'll go ahead and change it over here to 180, which is a bit more what I want. You can also modify these numbers as the game is playing, right? I can say, oh, what about a speed of 10? And then plug that in. Like, wow, that's super fast. Keep in mind, as soon as you stop the game, it's going to erase the changes you made while the game is running. Okay, so we got a ship rotation going on, which is great. I said that in the last video, that in this video, we would be looking at certain questions about the screen. Right now, the camera does not move with us, so we can move off the visible area of the screen. What do we do to change this? Well, in some games, you might want the camera to, well, there's a few different things. In your sort of vertical scrolling shooter, you're going to want the ship basically to move forward at a constant speed. Or maybe it's more like, almost like the camera moves forward at a constant speed and then the ship still can't exit the camera area. But of course, in that sort of shooter, you wouldn't be turning right and left like that. That sort of shooter, instead, what you do is you sort of, whoops, not that way. You move this way, vroom, vroom, from the left and right side of the screen, right? So that's not really what we're doing here. So what we might want to do is we might want to have the camera follow the player, stay locked on, if we had a large area to wander around. So one very naive way you can do this is by putting the main camera as a child of the player ship. Okay, and I'll make this really obvious to see what's going on. I'm going to go and drop an enemy in the scene, so we've got something sort of static to keep an eye on. Now, if I hit play and I move my player forward, you can see the camera chases the player. So in effect, because of relative stuff, the player will still stay in the middle of the screen, and then as I hit the forward key, the whole world will sort of move around you. And that might be fine. You don't generally want to do this particular version of it, though, because something really weird will happen as we rotate, right? Because the camera is sort of also rotating with the player, so it may or may not do the thing that you want it to do. So what we'd actually have to do is write a quick little script. So we deparent the main camera and the player. Okay, we have them be individual. And what you do is you create a little bit of a script that says, I guess we can make it now. I'm not going to use it in my version. We're going to say something like, we're going to call the script like something like follows target? I guess. Or we'll just call it camera follow or something like that. So new script, I took the lazy way here. So we create a new file. You can see it was added there. If I double click on this, it'll open up in mono develop, which is here. So what we're going to do, we don't need the start. We're going to do something like, we're going to make a public transform my target. I'm going to go really fast because I'm not really using this. I'm just going to demonstrate it. If my target not equals null, so assuming we've actually gotten our target set properly, if my target's not equal null, then what I'm going to do is set my position to be equal to the player, my target's position. So, I'll do it the wrong way first. So transform.position equals my target.position. If I do this, this is on the camera script, and you can see it's got a target, requires that. If I put player ship in the my target of the main camera, I hit play, something terrible is going to happen. Everything disappears. Why is that? Well, because we're copying the player ship position exactly, which is 0, 0, 0. Now our camera's got a 0 in the z-axis, which is why you can't see anything. So instead of naively doing it this way, what we're going to do is grab something like vector3 targ position. You're going to set the target position dot z to be equal to my current z, so that, so that we don't accidentally overwrite that. And then we're going to set transform position equals targ position at this point. So now if I do this, what'll happen is no matter where the player goes, the camera's coordinates will keep matching the player. The advantage of doing this way is if I rotate, the camera no longer rotates because we're not copying the rotation. Now, that's not bad. I think we can all agree that that's kind of cool and badass. Yeah. All right, so what I'm going to do is I'm going to leave that in here. I'm going to remove this script from the camera, but I'll go ahead and leave the script in the project. So when you guys download the project, that script will still be there. Because depending on what you're trying to do, that might be the answer. You can also, if you want to be even more sophisticated, instead of copying your transform instantly, you can use some sort of a lerping, vector3.lerp, to slowly sort of chase the player. So if the player's kind of far from the camera, it'll like rubber band you towards that. And it'll actually look kind of neat. Sometimes, maybe, it depends on what you're trying to do. I'll leave that one up to an exercise to the viewer. But here, consider using vector3.lerp for neat effects. There we go. So we're going to close that script. In our particular thing, we're going to do like the asteroid style thing, where the player is constrained to the play area. Okay? And we're going to do that for lots of reasons. The code that we're going to develop for this would be useful for your camera follow version as well. So our player ship, we don't want it to leave the screen. Okay. So how on earth do we do that? In our player movement script over here, after we've got our position, okay, we want to make sure this position doesn't bring us outside the bounds of the camera. So how do we do that? Restrict the player to the camera's boundaries. The first and easiest way to do this is to consider the height, the Y thing. We already talked about, in the very first episode, we talked about the camera's orthographic projection. Because it's an orthographic camera and it's got a size of 5, the distance from the middle of the screen to the top is 5. In fact, we can test this. If we grab our player ship and we set it to a Y of 5, you can see that it is on the boundaries of the screen. And specifically where? Well, we've got our little pivot point, our center point. The center point is exactly on the boundaries of the screen at the top. And if we set this to -5, same thing. The pivot point is exactly on the boundaries of the screen, but at the bottom. Okay, we can do something with this. Restrict the player to the camera's boundaries. So we can say something like, if position.y is greater than what? Well, it's the camera's orthographic size something or other. Okay, how do we get the camera? Well, the easiest way is to do camera.main. We're going to grab the main camera. Now, how does Unity know what the main camera is? You could have a scene with more than one camera. And sometimes we'll write this code and people will say, this doesn't work. It's giving me some sort of error. Your main camera is the camera with the tag main camera. If, for some reason, you deleted this camera, you can add it back in. I can go create camera. You can add a camera back in, that's fine. By default, your cameras are untagged. The main camera is the one that has the tag of main camera, okay? I know, I keep saying the same thing, but people will get this wrong. If you have something tagged as main camera, then camera.main will return that, okay? So, if the position of the player ship in the y-axis is greater than the camera.main.orthographic size. The orthographic size of the camera is 5. If our y is greater than 5, then we're clearly getting outside the boundaries, aren't we? Let's go ahead and give this a quick test. If it's bigger than this, then let's set our y to be equal to the orthographic size. Let's see what the heck this does. I'll hit play. I will move up, and boom, boom, boom. We hit the edge. It doesn't let us go any further than that. All right, we're good. Well, we're close. We're not entirely right, are we? Because we really don't want any part of our ship going off the edge of the screen, probably, I think. How big is our ship? Well, we could guess. We could give it some sort of number, but we're not going to do that. No, what we want to do is find out the bounds of this ship. And there's a few different ways of doing this. Let me think in terms of what I did last time. I did anything like this. Because you can do bounds. Bounds was a weird way of saying it. You can do boundaries based on the renderer size, the collider size, all kinds of things like that. I'm cheating a little bit. I'm checking to see. Last time I did something vaguely similar to this. I'm just trying to see what I did. Putting it side by side. Did I use the collider? No. No, I put in the fixed number. All right, that'll be fine. We'll do that for simplicity. I like that. So we're going to go ahead and we're going to figure out some sort of like radius around our ship that we want to not bounce off of. And let's call it something like float ship boundary radius. And we'll give it something like, I don't know, just like a half a unit or something like this. Well, it'll be a bit of trial and error. We can talk about exactly how we're going to do this with colliders later on. We don't have colliders on our ship yet, so we can't really use any other means, really. The renderer thing is a little bit weird. So ship boundary radius of like a half a unit. We're going to just guess. And that's how far away the edge we're going to be. So here, our position not y, we really want, if our position not y plus the size of our ship is bigger than the orthographic size, then set our position not y to the orthographic size minus the size of our ship. So now it should keep us a half a unit away from the edge of the screen. Ooh, almost works out perfectly there, actually. That's pretty good. Let's do the same thing on the bottom. If the position.y less the ship boundary is smaller than the orthographic size, then set our position to the, no, it is smaller than the negative of the orthographic size. So set our position to negative orthographic size plus boundary. We're just reversing all the signs for the other side because we're talking about -5. And so now if we go here, yeah, that's nice. And we can't back into it either. Good. All right, that's pretty good. Now, because we're not using the collision box, it's not necessarily automatically pixel perfect, but damn, wow, that's pretty nice. Now, if we did change the boundary size, let's say we change this to a 1. Now it'll keep us a little further away from the edge than before, right? Now there's a bit of a gap. I quite like the 0.5, actually. It worked out very nicely. It was very coincidental because the other project I had was very different and used very different graphic sizes. But it was still a sort of a spacey moving around thing, so I guess there was some nice crossover there. All right, that's great. Now, how do we do the edges? Right, we've got the top and bottom. How do we do the left and right? Well, the problem, as mentioned before, there's no one variable we can read for the left and right edge because there's only, the orthographic size is only the verticality of it. And the rest of it is sort of, I don't know, dynamic-ish kind of thing based on the width of your viewport. So how do we figure out what the edges on the side are? Well, we can figure out what the ratio of our screen is. And what do I mean by that? Well, the old school screens, right, your square monitors were these 4:3 ratios. It was 4 units wide this way to 3 units wide this way. So something like 640 by 480. If you divide 640 by 480, you get this 4:3 ratio. So it would have been 640 wide, 480 this way. Widescreen monitors tend to be 16 by 9. Some of them can be 16 by 10 as well. And then there's free aspect. Then you've got tablets and things like this, which can come in all sorts of shapes and sizes. So we need to figure out what that ratio between the height and width is. Well, we can find that out. So we can call something like screen ratio is our screen dot width divided by screen dot height. Usually your screen will be wider than it is tall, so this will be a number that is usually above 1. Now, this is actually going to lead to a bit of a glitch here. Warning, will be weird. And I'll explain why in a second. So, we've got the screen ratio. So now, our sort of width ortho, which sounds like a word I'd use, is the camera orthographic size multiplied by the screen ratio. If the screen, for some reason, is thinner than it is tall, then width ortho will be smaller than orthographic size. Generally speaking, the width is going to be bigger than the height. Therefore, this number will be bigger than the normal orthographic size. But other than that, our stuff is exactly the same. I can go ahead, copy this, and then what I'm looking to do is change all these y's to x's. Right? X. Thank you, pop-up. You're being really relevant and helpful here. X, we're going to use, that sounded dirty, we're going to use width ortho everywhere here. Okay, and that should work for our horizontal. Let's go and give it a test. Keeping in mind, warning, this will be weird. It's not going to work quite right. Look, it's stopping us here. We don't want to be stopped here. We want to be stopped over here. If I make it a little bit wider, what happens? Oops. And then put my context back over there. No, there we go. And then, okay, that almost works. But then if I make it wider, it's like, no, what's going on? Why is it weird? The reason it's weird is because screen width and screen height are integers. So when you do division or any math with integers, the number returned is an integer. Then we stuff it in a float, and then at that point it becomes a float. But what's the implication here? Well, when you divide an integer by an integer, you get a whole number. So while this ratio, here, for example, 16 by 9, should give you a number of, I don't know, is that like 1.333? Something like that. Listen, don't do math on live TV. It never goes well. Maybe the number is supposed to be 1.333. But because we're doing integer math, that just gets truncated down to 1, which is why the screen ratio is not quite right. So we need to force this math to be done in sort of floating point stuff. So what we're just going to do is cast our width and height to floats. And now we'll get a proper decimal answer of 1.33 or whatever it's supposed to be in screen ratio, which will fix the rest of it. Let's go ahead and hit play. Now I can go back to free aspect as well. And hit play. And now we should hit the side boundaries exactly like we hit the top. There we go. And if I go ahead and switch this, boop. Actually, it'll even update that way, although not that way. Boop. Very nice. Okay, now we've got screen boundaries. I think we can say that's a pretty big success. First, do vertical because it's simpler. Now, calculate the graphic width based on the screen ratio. Now, do horizontal bounds. There we go. Finally, update our position. Hooray! All right. So there we go. So that brings us to there. Next episode. That's when some exciting stuff starts to happen. Our enemy over here, we're going to start being able to bump into it. We're going to look at colliders. This enemy's not going to do anything to start off with. It's going to be, oh yeah, and that's, I do have to add a whole other episode to get the enemy moving. I forgot all about that. We're going to add some colliders to this enemy and have our spaceship smack into it, have them both die, and also we're going to have our spaceship shoot some bullets, pew, 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 and blow up the enemy. See you next time, folks. Bye-bye.